differentiating series to generate a new function. So we can start with, we're going to show the example here where we're going to start with this series for a sine function. And that's this series right here. Okay, this is a known series. This has been given to us previously. So we're going to start with this known series. And we're going to differentiate it to generate a cosine series. And we could do this because the derivative of sine x is equal to cos x. Well, that means then that if I differentiate the series for sine x, so this series here represents sine x, if I differentiate this series that represents sine x, I'm going to generate a cosine x series. Okay, so that's what we're going to try to do. And we can also generalize this by saying that if we start with a known series, we can actually generate new series by substitution, differentiating and integrating. So substituting, differentiating, integrating will generate new functions if we have a known series to start from. So the known series that I'm going to start with is this sine series, -1 to the power n. So it's an alternating series, 2n plus 1 factorial, x to the power 2n plus 1. Notice that that power is always going to be odd. It's because sine is an odd function. So here is we're going to differentiate the series of sine to generate the series for cosine. And so I'm starting with my generalization for the sine. And I have also the expansion here, which I can compare. So this expansion here is all these terms. So when I plug in n equals 0, I get x to the power 1. N equals 3, I get x cubed over 6. Negative x cubed over 6 plus x5 over 120. And it's alternating like that. Okay, so differentiating this, when I differentiate this, I'm going to end up with a cosine function. So I'm going to say that cosine x is equal to whatever series I'm going to end up with here. So n is 0 to infinity. Now I'm just going to make a note that sometimes that n will change if we have constants in our expansion. In this case here, the same number of terms in the derivative as there are in my original function. So I'm going to differentiate this. So -1 to the n does not differentiate. 2n plus 1 factorial doesn't differentiate. This power differentiates using power rule. So 2n plus 1 is my power. And then I'm going to reduce the power on x by 1. So I'm going to end up with 2n. And notice that my cosine function has an odd power because it is an even power because it's an even function. So there is my series for cosine. I'm just going to simplify this. So that 2n plus 1 factorial, I can rewrite it as 2n plus 1 times 2n all the way down to zeros, or all the way down to 1, so I get 2n factorial. Notice that the 2n plus 1 for my power rule is going to cancel out with the 2n plus 1 here. So my simplified series is going to look like this. N equals 0 to infinity, alternating, so -1 to the power n. The coefficient is going to be divided by 2n factorial. And the power series part of this, the power part of it, is going to be all even powers. So if I were to do this expansion, when n equals 0, I get positive 1 minus, when n equals 1, I get x squared over 2 factorial, which is 2, plus when n is equal to 2, I get x to the power 4 over 4 factorial minus ... And that expansion I can use to calculate cosine. And I have my series expression here, my general series expression, which I can use for my ratio test to calculate radius of convergence, my interval of convergence.